So in this video, we're going to consider the question, how does pressure vary from point to point in a static fluid? And we're going to derive an equation to describe this. So to do this, we are going to consider a rectangular element of static fluid. So we'll first establish our coordinate system here. So we have x coming out of the page, y going to the right, and z going vertically upwards. And we're going to draw a little cube, a little element here that's a cube. And be sure to leave yourself some room around it. Okay, so here's our little cube, and our cube has dimensions of dx on this side, dy on this side, and dz vertically. So here's our little cube that we're going to consider, and this cube has a pressure of P at the exact center. So we will make a note of that. So the pressure at the center is P, and P is a function of x, y, and z, because we are considering how pressure changes with different directions and different areas. So how can we represent P at the different faces? So we have P in the center, and we're interested in expressing P, or getting an expression for P at the different faces. So the front face, the top face, the side faces. And so the way to do this is that we're going to use a Taylor series expansion to determine the pressure at each face. And when we do this, we're going to ignore the higher order terms and the reason we can do that is because the element is small. So we'll start off with the right face. We want to know what this pressure on the right face is, pushing on this cube. So we'll start off here. For example, the pressure on the right face is given by, and we'll call this P sub r, is equal to P, this is the pressure in the center, plus del P by del Y, which is an expression for how the pressure is changing in the Y direction, right? So as we go in the Y direction to the right, pressure is changing in some way. And it's changing in some way with the direction y. So we say del P by del Y multiplied by, and here we're going to say y sub r, which is the location of that right face, minus y, which is the location of the center of the cube, plus those higher order terms. And this is essentially equal to P, which is the pressure in the center, plus del P by del Y multiplied by dy over 2. dy is simply this distance right here. And so we're saying that the right-hand face is half of that distance from the center. So that gives us an example here to go by. So that's the pressure at the right face, but what is the force? So the force here we can write down as P plus del P by del Y times dy over 2. That's our pressure. And a pressure multiplied by the area gives us the force. And so we're going to multiply that by the area of this face, which is, of course, dx times dz. So this is the force on the right-hand face, and we can do something similar for the force on the left-hand face. So here we're going to have a similar expansion, but this time we'll say P minus del P by del Y, again times that distance, dy over 2. So that's our pressure at that face, and we're going to multiply that by the area of the face, which is dx dz. And so now we have the forces on the left-hand side and the right-hand side, and we can do something similar for the force on the top. So here we have a force on this top face from pressure, where we have the pressure described as P plus del P by del Z. So this is the gradient of the pressure in the Z direction going up, multiplied by that distance, dz over 2. And that's the pressure at that top face. And we multiply that by dx times dy, which is the area of that face. And we can do something similar now for the pressure or the force on the bottom. So we have here P minus del P by del Z multiplied by that distance, which is again dz over 2, multiplied by the area, which is dx times dy. And we could do something similar for the pressures and forces on the front X face and the back X face, but we're not going to go into that detail. So we're just going to look at the forces in the Y direction and sum up all of those forces now. So then the total surface force in the Y direction, and here I'm making a note that we're just looking at surface forces. We'll come back and look at body forces later. So the total surface force in the Y direction is dFy is equal to P minus del P by del Y times dy over 2 multiplied by dx times dz. So that's the upward pointing force on the bottom of the cube. And now we have the top force, which is pointed downward, so we have a minus sign here. So minus P plus del P by del Y times dy over 2 multiplied by dx times dz. And when we do this, we see that this pressure term cancels out with this pressure term, and we're left with some terms that combine with each other to get minus del P by del Y times dx dy dz. So the dy over 2 and the dy over 2 have combined to give us this expression here. So this is the total surface force in the Y direction, and we can do something similar for the X and Z directions. So for X and Z z directions, the surface forces are fx. These are vectors here. That's why we have the arrow on top. So we have minus del p by del x times dx, dy, dz, and df is equal to minus del p by del z times dx, dy, dz. So we would get these from the exact same procedure that we went through to find the total surface force in the y direction. Now we have the total surface forces in the x, y, and z directions, and so we can combine those into one single expression. So we can say that the total surface force is df sub s equal to, and here we're just adding together our three terms, equal to minus del p by del x in the I direction plus del p by del y in the j direction plus del p by del z in the k direction. And these are all multiplied by dx, dy, dz. Now I'll write it this way because this term in the parentheses here is something special. And that is, in fact, the gradient of the pressure. So I'm going to make a note of this, that the term in parentheses is called the gradient of the pressure. And there's a couple different ways to write this special term. So sometimes you'll see this written as grad P, like this. So GRAD stands for gradient. But oftentimes you'll see it written in this notation with an upside down triangle, which is the symbol for del. So this is pronounced as del. And that stands for the gradient. And so this we can write this out as del p by del x of I plus del p by del y of j plus del p by del z of k. And so this is the gradient of the pressure, but we can also sort of separate out that gradient operator and write the gradient operator as simply del by del x in the I direction plus del by del y in the j direction plus del by del z in the k direction, and we can apply that expression to P. So these are a couple of different ways to write the pressure gradient. But the point here is that the surface force is equal to minus of the pressure gradient multiplied by dx by dy, or dx, dy, dz. And so we can write that out as df sub s is equal to minus del p dx, dy, and dz. So that is the expression for the total surface force, and that encompasses pressures in the x, y, and z directions. So those are the surface forces, and now we can add in the body forces. So now let's add in the weight, which is the body force. So we did not mention the weight before, but of course that cube a fluid has a weight. And so we can go back up here to our drawing here, and we can add in the weight. Now the weight here we can write as W is equal to gamma, which is our specific weight, which again is a force per unit volume. And we can multiply that by the volume of the cube, dx, dy, dz, and that will give us the weight. So that's our expression for the weight of this cube. So as I said, the weight of the element is negative dw in the k direction, or the z direction, is equal to minus gamma dx dy dz. And again, that's in the k direction. So now we have our forces. We have our surface forces, which are pressure, and we have our body force, which is weight. And now we can apply Newton's second law to this element. Okay, so we're going to sum up all of the forces on this element, and that's equal to the mass times acceleration. And here the d's represent some differential mass. In this case, the cube is a very small cube that we're applying it to, and so that dm is, of course, equal to the density times the volume. So this is just an elemental sort of differential little cube that we're applying this equation to. And so now we can plug in our values here. So our expressions. So the sum of forces is equal to our surface forces, and then we have our body forces, which are negative, which is negative, I should say, is equal to our mass times acceleration. Okay, so putting in our body force, putting in our surface force first, which is up here. So we're going to put that in first. We have the pressure dx dy dz minus, and what comes next is, of course, our body force right here. So minus gamma dx dy dz in the k direction. And this is equal to our expression for mass times acceleration. So that's right above here. So rho dx dy dz multiplied by the acceleration. And what you can see, of course, is that our volume cancels out. Dx dy dz cancels out of all of the equations here. And we're left with the general equation of negative del P minus gamma K is equal to rho times acceleration. This is a very important equation. This is our general equation describing how pressure varies in a fluid, in a static fluid. Now, a couple of simplifications here. If our fluid is at rest, then our acceleration is, of course, equal to 0. And if that's the case, then our equation simplifies somewhat to negative del P is equal to gamma K. Or we can also write that as del P is equal to negative gamma K, which is the more usual way to write this. And so this describes how pressure varies. We have the pressure gradient is equal to negative gamma K. But this tells us that del P by del X and del P by del Y are equal to 0. So this tells us that pressure does not change in the X or Y directions, but in the Z direction, it changes in a very particular way. In the Z direction, del P by del Z, and here we can change the partial derivative to a regular derivative to say that dP by del Z is equal to negative gamma. So this is an equation or an expression that we will use quite a lot. This is basic pressure-height relationship of fluid mechanics. And so we can rewrite that again as equal to negative gamma. And of course, we remember that negative gamma is equal to negative rho g. And so this just tells us that this is equal to a constant for an incompressible fluid. So as long as the density of the fluid isn't changing, that's what we mean by incompressible, then this expression will hold. So that's our basic pressure-height relationship for fluid mechanics and for fluid statics, and we will pick up on that later.